All right. So thank you everyone for coming today. Today it's going to be a little different than a review course you've probably been to. Essentially, we're trying to cover the entire course today, which we will do. So we'll basically give you a little refresher. We'll go in depth to some tricks, some hacks that you can do to make the exam easier, and then there'll be a few practice problems that we can work through together. Emphasis on together because yeah, but it'll be pretty fun. So thank you everyone for coming. By the way, if at some point you're like, nah, I don't need this, or like, nah, this sucks, you're free to go. I won't keep you here. It'll be recorded on YouTube, so you can watch it in 2 times speed, save you time. Anyways, Math 100, let's go. All right, so we're starting off from the basics, talking about the limits. Essentially, when you're looking at a limit, imagine you've probably done this before. You're going to your nose, right? So you want the left side limit to equal the right side limit, and therefore that limit will exist. In the first example up there, ooh, I have a laser pointer. You can see that the left side and the right side both come together to equal the same value, even though that value isn't defined. That is a-okay. That limit exists. But in the middle example, it's not defined at x equals 2 because as you come over from the left side, it equals 2. And as you come over from the right side, it approaches, I don't know what that's like, -9. So that limit would not exist. And then obviously a straight line, that limit is going to be defined everywhere. Does that make sense? So for the definition of a limit, all you're looking for is whether the left side of that limit equals the right side. That is how you know that the limit there exists. What are some ways of solving limits? So there's, I think, 7 kind of ways of solving limits. The first thing that you should always try is direct substitution. Okay? So that is where the limit as x approaches a value, all you do is you plug in that value into the limit, and then you see what that returns. If that returns 0, you're good. You're chilling. If that returns infinity over infinity, you're not good. You're not chilling. You got to do something else. All right? So those are called indeterminate forms. There's a bunch of them there. Really ignore everything after the first 2. All right? So infinity over infinity and 0 over 0. Those are the main ones. If you remember those, you should be fine. All right. So you've plugged it in. Here, all right, we plug it in, we get 4 minus 4 on the numerator, which is 0, which you might start, being a little nervous. But then on the bottom, you have the square root of 2 minus 3. That's like some negative number. So it's just 0 over a negative number. You're good to go. But let's say that that was actually 0 over 0. Now, there's some other things you can try. You can try factoring. So this is the next thing you should try. So if you see kind of 4 different terms, or you see 3 terms that look like a polynomial that would be easily factored, you, for the most part, will be able to factor that out and then divide out the denominator, which then leaves you a term which isn't like rational function, and then it'll just be 0, or it'll just be a number, and it won't be 0 over 0. Does that make sense? Okay, those are the easy ones. There's a few more complicated ones of solving limits. So if you're seeing fractions on the numerator, probably it's going to be use a common denominator. So all you do is for the one in that example, you're going to multiply by a common denominator. So it would be 1 over x times 2 minus 1 over 2 times x. And then you'll be able to evaluate that. Let me know if you guys like, I can work through some of these, but I feel like it's a little more so review for you. And then that'll basically allow you to, again, cancel out the denominator, which is what you're trying to do in the end, and then you'll no longer have an indeterminate form. The next type, which is pretty common, if you see a radical, odds are it's going to be multiplied by the conjugate. What that is, it's a little bit of difference of squares, but basically you're multiplying both the numerator and the denominator by essentially the 2 terms, but instead of having a negative sign, you have a positive sign. Or instead of having a positive sign, so basically you're getting rid of the radical by squaring it, like doing the difference of squares. So then on top, rather than having the square root of a function, it would just be x squared minus 4x plus 20 minus 4 squared, which would be 16. And then now your denominator will have that radical term, but rather than a minus, it'll be a plus. So then the denominator will increase in value because it's not going to be multiplying by 0 because it's a plus sign instead of a minus sign. Another way of solving limits for when there's an absolute value is using the definition of it, so one-sided limits. So this is primarily for absolute values, but just remember that the absolute value of x when x is less than 0 just equals negative x. Oftentimes when you're seeing functions and there's absolute values, it's kind of scary and I don't like them. But if you just substitute if you know that x is going to be less than 0 over a certain range or a certain interval, you can just substitute that absolute value of x for negative x, and it will make it look a lot nicer and a lot simpler. The other trick, which is actually, I think, most used, I would say, is for when you're going for a horizontal asymptote, or when the limit as x goes to positive or negative infinity. And there's kind of two tricks for doing this. One is multiplication by the highest power, and the other is factoring out. Multiplication by the highest power is essentially if you have I'll do an example. This will be good. Essentially, if you have like x squared minus x over x squared plus 1, you'd be multiplying both the top and the bottom by 1 over x squared, which is basically just multiplying by 1. And then what this will give you is it'll give you x squared over x squared minus x over x squared. So then this will reduce to just a constant, which would be 1. But then this, since the denominator will grow exponentially large, faster than the numerator, that will just approach 0. So you can ignore it. So that's kind of the trick that you use with multiplication by 1 over the highest power. And then the second trick, which is really helpful for radicals, is if you have a radical on top, we'll just say that. It might be a little confusing for evaluating this, but if you imagine you're factoring out this portion of the radical, so you're factoring out a square root of x, and then you're left with what you have to multiply in. So that would be 1, and then plus x over x squared. So this is a really handy trick for complicated radicals, but basically then if you multiply this, now this term will be x squared, and then this term will be x, which is what you have before, and then square root of x is just x, so then you can do like highest powers. Does that make sense? Any questions on that? Okay, sick. Lastly is L'Hopital's rule. Also, if I'm going over anything too quickly, just ask me to clarify. I won't judge at all, I promise. I know I can go quick sometimes. But yeah, okay. So the next one, the last one, is L'Hopital's rule. You don't have to use it, but if you do use it, there are just a few things to keep in mind. First, it has to be in an indeterminate form. So either 0, 0 or infinity over infinity. Those are the only two indeterminate forms that it will work for. And then the second thing is as you take L'Hopital's rule, which if some of you aren't too familiar with it, basically you'll have a rational function. Let's say it's f of x over g of x. And then all it is that limit will equal f prime of x over g prime of x. And then you can keep doing that. So you'll have f double prime, f triple prime. You keep doing that up until the limit exists. So that's essentially the premise of L'Hopital's rule. But what they teach is there's just a few things that you have to kind of state in order to use it. One, you have to state that it's in indeterminate form. So just write a little thing. This limit is indeterminate 0 over 0. That's the first part. And then the second part, it's kind of a little circular. After you've taken L'Hopital's rule and done it multiple times till that the limit exists, then you just have to make a statement, because the limit exists, L'Hopital's rule works. It's circular like that way, but basically if you put those two statements, you should be fine. You shouldn't lose any marks for using L'Hopital's rule. The one thing to note is that you can't prove a limit doesn't exist with L'Hopital's rule. So if through doing L'Hopital's rule, your limit doesn't exist, you have to try another way. You can't just say limit doesn't exist because L'Hopital. And then the last one is kind of what we did over here by multiplying by 1. If you just have a function that's not a rational function, but you want to use L'Hopital's rule, you can multiply it by, and it's not in like one of those indeterminate forms, you can multiply it by 1, so like x over x, or whatever that may be, to reduce that. So kind of an example would be if you had like ln x, and you'd essentially want to change that into indeterminate form, you could just multiply it by like x over x, and then that would give you a rational function. So essentially, always remember you can multiply any function by the same number over the same number, and that'll give you a rational function that you could use L'Hopital's rule for. Any questions with that? It's just a helpful trick if you have to solve a really complicated limit. Okay. So there's two limit definitions of the derivative, which I almost guarantee there will be a question, I feel like, about this. So for the general use where you're not specified a case, that's the f of x plus h minus f of x all over h as h goes to 0. But then if you are given a specific point, that's where you can use the limit as x goes to a, and that'll just simplify things, especially if a is 0. That's really helpful. But these are, you guys have probably done these before, so I'm just, as a reminder, if a specific point, use the one to your right, general use, use the one on the left. But then they're more so useful for when there's questions about whether or not a function is differentiable at a specific point. So a derivative is defined if, one, the limit definition of that derivative exists. So if this limit exists, that's the first step. And then the second part is that the function has to be defined at that point. For the most part of functions, these are the two kind of things to show that a function is differentiable. So if a question is asking you whether or not the function is differentiable, one, take the limit definition of the derivative, prove that that exists, and then show that the function is defined at that point. And for it to be defined, you're just evaluating f at a certain value. And just on graphs, there's a few ways for a derivative not to exist. So at kind of a cusp, at a discontinuity, and then also at a vertical tangent line. Those are just a few examples graphically where the derivative wouldn't exist. Are there any questions about that? Okay. So primarily you'll see this with.
Can you give an example of where you actually get a cusp?
On the second midterm of flavor C, there was a question where you had to, it basically gave you the graph of the derivative, and then you had to graph the function, and it ended up being a cusp because to the right of a certain value, it was concave up, but increasing, and then to the left of that, it was concave up, but decreasing. So those two concave ups made a cusp. Okay. So it's not, I don't know an exact function, but if they give you like graphs, it can create that cusp like. So this is kind of what we were talking about. In order for it to be differentiable of a piecewise function, you're kind of doing those one-sided limits. So you'll be the limit definition of the derivative of the left side equals the limit definition of the right side, and then also the function is defined at that point. These are a few common questions, especially in the past midterms. They'll kind of ask you, show that this piecewise function is differentiable at a point 0. So the derivatives must equal each other, and then the function must exist at that point. Then you know that it's differentiable, and the derivatives also have to exist. Okay. Really quickly, the few derivative rules. So there's power rule, product rule, chain rule, quotient rule. I'm sure you guys have seen these before. Just keep in mind with a chain rule, you want to start from the outside in and then work your way in to the middle. Quotient rule, it's essentially like similar to the product rule, just don't forget that it's a negative sign instead of a plus sign, and then you can apply the product rule multiple times. The next thing with derivatives is implicit differentiation. This has kind of been gone through, but just kind of a few tips to keep in mind is when you're doing it, rewrite f of x as y. It'll make things a lot simpler. And then also, rather than using like dy over dx, I suggest just doing y prime, so you don't have to write more, and then it doesn't get super messy when you're having like 5 different y prime terms and you don't know what is what. And then always remember, after you do that, that y is a function of x. So when you differentiate y, use the chain rule. You're always going to have whatever it is, like y squared. That would be 2y times dy over dx, or times y prime. And then after you implicit differentiate, you'll want to isolate for dy dx through common factoring and rearranging. And then also just watch out, sometimes on a few of the midterm questions, they'll trick you. Rather than saying for we want dy dx, they'll ask you for dx dy. So that implies that x is a function of y, as opposed to y being a function of x. So it's essentially the same thing, but suppose up there it was just, this would equal just 2y, but if that was x, yeah, so just make sure you understand whether or not they're asking you for dy dx or dx dy. So if they're asking you for dx dy, x is a function of y, and it's basically just like they're flipped. Okay? And then the next one is logarithmic differentiation. This is when you have kind of a function to the power of another function, and it's used to simplify this. So essentially, as you can see in that example here, we have a function, and it's to the power of another function. So in order to simplify this, we take the ln, or the natural logarithm, of both sides, and then we implicit differentiate that. So by doing what we kind of did before with ln of y, that would be 1 over y times y prime. And then on the right side, you're able to bring down that exponent in front of the natural logarithm because of exponent laws. Yeah? I'm so glad you asked that. So essentially, when you're like natural log differential, you can imagine it, since it's not multiplied by, it's plus, you can almost isolate the edx as a separate like function. So you can take the derivative of the first part of the function and then add the derivative of the second part of the function. So you don't actually have to include like e to the x in it. You can just, yeah, you can just like keep it separately. So it can help in your equations. Because if it was 1, it would multiply like the e to the x outside. So those are pretty cool. And then simplify it afterwards. Okay, and then lastly, kind of inverse functions. Just quickly going over, it's basically, rather than having x as an input that returns y, you have y as an input that returns x. So if the f of x equals 7, then the inverse of 7 would equal x. And in order to solve this, all you do is you write f of x as y, you swap that y in x places, and then you rearrange and solve that equation for y. And that's all it is for inverse functions, and you can also differentiate that. Yeah, and then derivative, you can use that to determine the derivative of an inverse function. Hopefully, you've memorized most of these derivatives, except just do the top 3. There's no reason to have to memorize cosecant, secant, or cotangent. You can derive those using chain rule and power rule. So what's the derivative of cos x? Who said sine? Who said sine? Yeah, okay, and then same thing with these ones. Just remember the top 3 basically. So derivative of arc sine is 1 over square root of 1 minus x squared. Arc cos is basically the same thing, but boom, there's a negative sign because the derivative of cosine is negative sign, yeah. And then arc tangent, you just don't have the square root. So just make sure you know those so you don't make a silly mistake on the exam. There's a flashcard set if you're interested in helping to memorize these. So you can take a photo of that if you want. The slides will also be posted afterwards. Okay, now this is actually, I don't know, this helps a lot. So we have a right triangle, and we want to find the derivative of sine of arc cos. We could do that using chain rule, but that's bad. That's not bad. That's the long way. I feel like I don't want to do the long way. So essentially, what we're going to do is we're going to use kind of a little trick that you can like, it's pretty simple, but essentially you want to set this angle as whatever your theta is. So in this case, that would be sine of theta, so sine of arc cos. So we're going to set this as arc cosine of x. Okay? So now that we know that this theta is arc cosine of x, we're able to determine where x would be, right? So can anyone tell me which of these sides would be x? Yeah. The bottom, exactly. Okay, so we know that this is x, but then we also know what the hypotenuse would be now, because it would be 1. Okay? So now we can determine what this is, right? Just using Pythagorean's theorem. So we can say that this side would be 1 squared minus x squared square rooted. Okay? Does that make sense? Yeah. So now, what would sine of theta be? It would just be 1 squared minus x squared over 1, opposite over hypotenuse. So then rather than having to differentiate sine of arc cosine, you can just differentiate this, which is a lot easier, right? So if you ever see kind of sine, arc, cos, you can simplify it using this trick. And that works. You can put arc sine, arc tangent, whatever you want as a theta. That really helps to simplify any like inverse trig functions. Are there any questions about that? Okay. Does that make sense? Okay. Oh, that's what I did. Okay, so those are just some steps in there in case you forget. You can look over and that's exactly what we did. So we did it right. Good job, guys. Okay, moving on to related rates. Damn, we're like speeding through this. All right, so kind of the steps to go through. First off, always write a let statement. You don't want to lose 0.5 marks because you don't define your variables and you also don't define your units of your variables. So just make it simpler, start with a let statement, and then after that, you want to write down everything you know and everything you need. Okay? Those are the first two easy parts. The hard part, is what's in red, is essentially you want to write the question as a singular function. So this, you might have to define a variable in terms of another variable. Yeah?
What if you can't do that because your function is really hard to...
Oh, I know exactly. We're going to get to that. We're going to get to that. Yeah. That's our next slideshow. We're using the example from your guys' midterm. Yeah. Okay. Or like I'm kind of explaining that. Anyways, and then after you have the function as a singular equation, you're going to implicit differentiate that function, rearrange it and solve for what you need, what you haven't been given, and then in your therefore statement, just make sure you include the units. And you can also use your units to double check because you know that like the derivative would be like units over units. So just make sure it's like milliliters per time or milliliters per second. So that's just a way to check it. Okay. But how do you determine the equation to differentiate? That's such a great question. Thank you, Daniel. So there's kind of three different main questions that they'll ask. The first is like geometric, so they'll give you kind of a cylinder, a cone, or a shape. So then you have a function of volume or a function of area. And then you can use similar triangles or kind of ratios of one side length to another side length to determine one variable in terms of the other variable. So for the example that we're going to do, you're determining r in terms of h. The second one is for distance. So this is kind of ships or police officers. You want to create basically as many right angle triangles as you can. And then you'll also have one side length if you're kind of cutting a side length in half. One of those side lengths will be x, and the other side length will be a constant minus x. So that's if you've seen the problem where you're on an island going to shore, where should you go on shore? One of those side lengths from where your landing zone would be x. The other side would be with the length of the shore minus x. And then the hard one is when you're given a function. So for the Math A second midterm, they were given some like chain, but the functions weren't related together. So basically, the best way that I've thought about explaining this is the functions aren't related in any way aside from that they have the same variable. But you know that you want dE, dL. But you don't know how to determine that. But you know that you have dE dA and dL dA. So how do you kind of get rid of dA? You divide it out. So you're able to divide out derivatives to cancel out kind of those units per se. That's what's actually getting canceled out. But to get to a derivative that you want. So in this case, you're dividing out by dA, so then it cancels out dA, and then you're left with what you want. So you're able to like multiply or divide out to get to the units of what you want. Does that make sense? Are there any questions about that? Because I know like during the midterm, I can imagine how stressful that would be when there's no relationship between the two functions, but sometimes even though it's like nicer to write f prime of x, sometimes it's better to write it like this, so then you can actually see where the units are and how to divide out the units. So if you're ever stuck, try writing it a different notation, and then you can see, how can I divide out these units, or how can I get it to the units that I want? I think that would be pretty helpful. Okay, linear approximation. Who did, ooh, that was fun. Ooh. Okay, so basically, the only thing to keep in mind is one, remember this. I feel like that's pretty important. So just make sure that you remember this. And then the second thing to remember is that the x in this equation is where you are approximating, and the a is kind of the number that you know what the value of the function would be. So I always like to use the square root of 9 example. So in that terms, 9 would be your a, and let's say you're trying to approximate the square root of 8. So you know that square root of 9 would be 3, so that's your f at a. And then you can evaluate the derivative of the square root at 9. And then here you'll have 8, here you'll have 9. And then just one way to check it is that you want to know basically if this is going to be a negative number or a positive number. If, let's say in this case, 9 is, you know the value of the function, 8 is smaller than it, so then this should be negative. But then if it was 10, that should be positive because you're adding on to the value of 3. So the square root of 8 is less than 3. Square root of 10 is greater than 3. And that's kind of determined by the sign of this, which is determined by the sign in here. So that's just one way of checking over if you've flipped the x and a's, if you've kept them the same. Just make sure, oh, am I approximating the square root of 8? Should it be greater than 3 or less than 3? Greater than f at a or less than f at a? Any questions about that? Yeah?
Can you remind me, does x stay as a constant? Like, does x stay as x and a is like the point they give you?
Okay, yeah. So the question kind of was if x stays as x. So this is the general form. So then let's say we'll use the same example. You want to approximate the square root of 8. So what's close to the square root of 8 that you know exactly what it is the square root of 9. So in that case, your x is kind of the point that you're trying to understand what the value is. So that's like the point you're guesstimating what its value is through this. A is the point that you know the value of the function at. Does that answer your question? Yeah. Okay. So Taylor series. Oh shoot, not this Taylor, not this Taylor. Oh no, Taylor series approximation. Wait. She's a pretty big performer. Okay, so Taylor series approximation. It's definitely pretty confusing, but there's just a few things to keep in mind, and there's honestly really only 2 questions that they can ask you. It's like, give the Taylor series approximation of a certain function, or if you're given a Taylor series approximation, what is the second derivative, or what is the third derivative? And there's just a few things to kind of keep in mind. This is the general form. So if you look, what do we have over here? Linear approximation, exactly. So Taylor series approximation is just added on to that. You're adding more terms to become more exact. So this is the general form. All it is you take the value of the function. So if you just did that, that would basically be a horizontal line plus the linear approximation. Now you kind of get like the tangent line to that. And then you're adding on the second derivatives. You're getting closer and closer to what it is. So a few things to keep in mind is make sure you're dividing by this exponent's factorial. So don't forget that. And then also remember, this is the value of the function that it's like you know, basically. And then this is the value of the function, or the value of x that you're getting close to, so what you're approximating. Okay, so approximate does not start with a for some reason. It would be really nice if it switched. So yeah, if you were given a Taylor series approximation, and let's say the coefficient of the third derivative is 3. Make sure that you understand that, okay, so that means that 3 equals basically the third derivative divided by 3 factorial. So make sure you're able to understand kind of, don't forget the factorial. That's very important. So it's always the derivative, whatever, like second prime, third prime, fourth prime, divided by that prime number factorial, and then your brackets are to the exponent of that number, okay? So keep in mind how many asterisks are here, the same number here, same number here. Very important. So yeah, this is an example I came up with just kind of help understand what it is. If you imagine Taylor Swift music, right? Each term you add is like one new note or one new word to her song, right? So in Shake It Off, if you add shake to start, you know, you're like somewhat there. And now if you add it, you're getting closer to the actual song. If you add, what other songs like crazy, haters, no, gonna hate, right? Now you get closer. So each of these terms is a new word or a new note. And the more you add, the closer you get to the actual song. And eventually, if you add them infinitely, boom, you get the song. Does that make sense? That's literally, that's, okay, but yeah. Okay, so how does that look graphically? So I just want to kind of show what I meant. So here we have just shake. Okay, this is just one word. This is just the F at A. Okay, now we're going to add, boom, linear approximation. All right, it's getting closer to what the actual function looks like in red. Now let's add another term. Boom, it's getting closer. It's getting closer. It's getting closer. It's getting closer. And if I were to do that infinitely, I'll go back because it's kind of cool. It's really satisfying. So look, that's pretty close, especially near 0. We're basically spot on, right? So that's only like the 6th series, I believe. So that's essentially how it looks graphically and also how it looks musically. Yeah. Okay. Now, time for Maclaurin polynomials, or as I like to call them, Maclaurin polynomials, because it's way more fun to say. So from now on, I'm going to be saying Maclaurin polynomials just because I think it's a lot cooler. All right, so essentially there's 5 things that you should have memorized. Just make sure that e to the x, it's always going to be positive. 1 over 1 minus x, always going to be positive. And then sine x is going to be using the odd exponents. And then cos x is going to be using the even exponents. So the first term of cos x is 1, which is x to the 0, and then x to the 2. And then sine x and cos x alternate, so they start positive, then they go negative, positive, negative. Same with log of 1 plus x. It's essentially the same as e to the x, but there's no 1, and it alternates. Okay, so positive, negative, positive, negative. Just memorize these to the best of your abilities. That way you don't have to figure out what they are on the final exam. Any questions about these? If you're struggling with memorizing the polynomial expansions, there's another flashcard set that you can use to memorize it, help you out a little bit. That would be good. So you can take a photo. The slides will also be posted afterwards. Okay. Curve sketching. These are just kind of what some of the common curve sketching will look like. So just make sure you kind of have a rough idea of what e to the x looks like, what ln x looks like, and understand what their domains are. So e to the x, right, can't be negative. Ln of x, the y value can't be negative. Those are inverse functions. And then, you know, x squared, square root of x. So just if you just understand and have a basic idea of how these functions look like, that should be good. Okay, so the steps to go through for sketching. First thing, you want to find the domain of the function. So that is where the x where like it exists essentially. And then you can check how will that graph look for large x and small x. That's kind of unnecessary. And then you also want to find the x and y intercepts. After that, you find any horizontal asymptotes, which is when you take the limit as x goes to positive infinity or as x goes to negative infinity, or vertical asymptotes, which is where the limit of f of x goes limit as x goes to something goes to infinity. So this is basically where the denominator would equal 0. So, but you'll do that with one-sided limits to understand whether it goes to positive infinity or whether it goes to negative infinity. And then you can also, once you find the roots or the horizontal x-intercepts, you can test whether or not on either side of them the function is positive or negative, and that will just help to give you a better picture of the function in its entirety. Step 2, you're going to take the first derivative of the function, and then critical points are where the first derivative equals 0. Singular points are where the first derivative does not exist. Both of these are potential for local min or local maximum or global min, global max, but it's not for sure. So just like for a cubic function, if I go back here, yes, there is a the like horizontal tangent line, but then the function just keeps increasing. So that's actually not a local min or a local max. So just because you have a critical point or a singular point, that's not enough to determine whether or not it is a local extrema, which is basically saying if it's a local max or a local min. Once you have these critical points and singular points, you're going to, like an easy way to do it is plot them on a number line, and then essentially you're testing values on the left and the right of each of those kind of roots per se, critical points and singular points, whether or not it's positive or negative. If it is positive, you know that the function is increasing over that range, and if it's negative, you know that the function is decreasing over the range. So let's say that this is 0 and this is 2, or negative 2, you can just test negative 1, and then you know that whatever value that returns of the derivative is going to be constant between these two roots. Okay? Yeah, so then make sure, also don't forget, where the derivative does not exist can be a local extrema. So make sure you're putting that on your number line. It's not just where the first derivative is 0, it's also where the first derivative does not exist. Once you determine that, that's where the function is increasing or decreasing. Next step, take the second derivative. Again, find where it's 0 or also where it does not exist, because again, that is a potential for an inflection point, which is kind of what we're looking for. Again, you're going to plot it on a number line, and then you test the negativity once again. If it is positive, it's going to be concave up. If it is negative, it's going to be concave down. And then you can combine those with what you know before. Put it all together, everything you know, and attempt to graph the function. This is kind of a table that you can look at. So basically, if you think of a u and an n and cut that in half, those are the 4 possibilities for what your graph can look like. A function can cross its horizontal asymptote, but as it gets very small or very large, so to negative infinity to positive infinity, it'll approach it, but it cannot cross its vertical asymptotes. And then if you're always stuck, you can always just test a few points. So you can test like, oh, what will negative 3 pi by 4 look? What will negative 2 pi by, like what will the points look like? And then you have points of reference that you can connect to help with your sketch. That is always a foolproof plan. Okay, optimization. Essentially, you want to find critical points, singular points, and endpoints of the interval. Once you have that, you're going to evaluate the function there, and then the absolute max and min will be like within that interval if it's closed. And yeah, so just a few key points about optimization. There's a difference between local minimum and global minimum max. So a function on a closed interval is guaranteed to have one of each for most normal functions of 1 global min and 1 global max. It cannot have more than one of those. That is the absolute minimum or absolute maximum or absolute minimum of a function. But a local minimum or local maximum is basically has to be either at a critical point or a singular point, or the endpoints. And essentially, what you're looking for again is where the first derivative is 0 or it does not exist. Those are the potential points. And you can use a second derivative test. So if the second derivative is less than 0, that's going to be a maximum. If the second derivative is greater than 0, that is going to be a minimum. Or you can also just see when you have this number line, if the first derivative goes from a positive to a negative, right? It's been increasing and now it's decreasing, so that's going to be a max. Similar for minimum, it's decreasing and now it's increasing, that's going to be a minimum. And also just keep in mind, at a critical point or a single point, it does not have to be a local max or a local min. It is not guaranteed to have extrema. In order to find global min or max, you have to evaluate. So once you determine, let's say you have a critical point at 3, you have to plug in 3 to the actual function, and then you'll compare all of your values of potential extrema. Your highest is going to be your global max. Your lowest is going to be your global min over a certain range. So just about those ranges. So if it's closed, you test the endpoints. But if it's an open interval, so that's denoted by kind of, rather than the square brackets, the curly brackets, you don't include the endpoints. So then it's possible for there to be no global extrema. Are there any questions about that? Okay. So a few other things. If the function is not continuous, sometimes this can mess up. And also if the function is unbounded. So let's say x squared goes up to infinity on both sides. It does not have a global maximum, but it does have a global minimum. But if you restrict that to a closed interval, then it will have a global maximum and a global minimum. So on an open unbounded, it's possible to have one, or it's possible to have neither, or it's possible to have both. But on a closed one, you'll have to have one and the other. Okay, a few small extra things just that can be helpful. So there's a thing called a small angle theorem. So essentially, if you have a trigonometric function, as x gets really small, it'll approach a value. So for sine, as x gets really small, it'll approach x. For cosine, it'll approach 1. And then since tan is just sine over cosine, it would be x over 1. So it would also approach x. This is handy for limits as x goes to 0. And it's also handy for limits as x goes to infinity, because this internal function will just approach 0. So you can say that this limit approaches 1. So that's just handy, and you can write down like small angle theorem, and they'll know what you're talking about. And this can simplify a lot of piecewise functions or other functions. Another thing, remember that for imaginary numbers, that is not included in the domain. If the denominator cannot be 0, because that would be undefined, so that can also not be included in the domain. And then you also just keep in mind, again, with the sketching, the domain of some known functions. So 1 of x can't be negative, and then also keep in mind what the domains of like the other functions are. And then lastly, when they say tangent lines, slope is the derivative at that point. So basically, when they're talking about, what is the slope, take the derivative and evaluate the derivative at that point. That is the slope at that point. A tangent line touches the function once and are horizontal when the first derivative is 0. Basically, that's all we have for today. Thank you all so much for coming.